Hey, this is Mr. Aiden. This is Pre-Calculus Honors, and we are in a new chapter. We're in exponential and logarithmic functions. This is one of my favorite things to teach because there's so many practical applications in the real world and in the world of science. We have exponential and logarithmic functions such as things like the pH scale with acids and bases, things like the decibel scale with the intensity of sound that you might hear, things like the coronavirus and the spread of the coronavirus. These are all exponential and logarithmic functions, and so there's so many practical applications. But we're going to start in 3.1, which is just looking at the exponential functions and their graphs. So let's get to it. We've been talking about algebraic functions from this point in the past up till now, and now we're going to take a look at some things called transcendental functions. And one of those transcendental functions, obviously, is the exponential function. Exponential function, what I mean is our function of x is equal to a, which is some constant that's going to be greater than 0, but cannot equal 1, and to the x power, and the x can be any real number. So let me give you an example. We have y equals 2 to the x power, 2 to the x power, and so when we have y equals 2 to the x power, and let's say x is equal to 4, y equals 2 to the 4th power, and what is 2 to the 4th power? Well, that is equal to 16. Okay, and so that's an exponential function. We could also have the function of x, or y, equals 16 to the x power, and let's say the x is the 1/2 power, so we have 16 to the 1/2 power. The 1/2 power is the same as the square root, or the second root of 16, which is equal to 4. Okay, let's take a look at the next one. We have y equals 4 to the x power, and let's say x is equal to -2, so 4 to the -2 power. Well, that negative exponent really just means that that bad boy is on the denominator, so that would be 1 over 4 squared, or 1/16. And let's say we have an irrational number like pi, 3.14159, blah, 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 blah. It goes on forever. It's an irrational number. How would you in the world find out what the function of x is if it's equal to 2 to the x power and that x is an irrational number? Well, what we would do is we would take 2 to the 3.1 value, and we have 2 to the 3.1 value, and we get 8.5741877 if you do that on your calculator. So then we have 2 to the 3.14 value, so 2 to the 3.14 value, and that ends up giving me 8.81524, so on and so forth. Okay, and then we would go 2 to the 3.142. Okay, and so on and so forth. And as you get further and further and further away, you'll see your limit will converge onto what is 2 to the pi power. So 2 to the pi power is going to be 8.824977827 dot dot dot. It will continue going on and on and on because that's an irrational number. But you can see we can get a good approximation of it from going to a more and more exact number of pi, but that pi number is irrational. It goes on forever. Therefore, we can't know exactly what it is, but we can know what it somewhat converges into the limit of. Okay, and so our example 1 is going to be graphs of these exponential functions. So you can see this green graph is 2 to the x value, and then you can see the blue one is 4 to the x, and you can see the red one is 6 to the x, which means 8 to the x. If we did 8 to the x, that 8 to the x asymptotes at 0, and you can see it'll be even more steep, won't it? So that would be 8 to the x power. But you can see they have all something very, very in common. When x is equal to 0, your y is equal to 1, isn't it? Okay, because anything 2 to the 0 power is equal to 1, 4 to the 0 power is equal to 1, anything to the 0 power is going to be equal to 1. So they all cross that point of at when the function is equal to 0, it equals 1. Okay. Take a look at what y equals a to the negative x power. Oh, one big thing is this is called a exponential growth function because it's growing. Whereas you can see in this case that y to the a to the negative x power, this is an exponential decay function. So this is decaying. Okay, and you can see that all when f of 0, it all equals 1, doesn't it? And you can see there it's all asymptoting at 0. It's never actually going to get to 0, but it's asymptoting at 0. And so those are your graphs of y equals a to the negative x power. So our example 3 is going to be transformations of our exponential functions. This is going to be kind of important to understand. So we have this is the graph of y equals 3 to the x power. So if you wanted to know what the function of y equals negative 3 to the x power, well, that negative in front of that function is going to literally take this and mirror it. Ooh, that is awful. It's going to mirror it to the x-axis. And so that would be the y equals negative, and I'll put this over here, y equals negative through to the x value. So if you put the negative in front, it mirrors it, it reflects it, and I'm going to put this here, it reflects it along the x-axis. That is if the negative is in front. But what happens if the negative is in the exponent? We've already covered that. That is where you're going to be a mirrored to the, oh, that's beautiful. It's going to be mirrored to the y-axis. So y equals 3 to the negative x power. When that negative is in right next to your x, your variable, it's going to be reflected to the y-axis, or along the y-axis. And so those are two big transformations that you can take a look at and you can be sure of. Okay? There's two other transformations that we can be sure of, and I'll do these in different colors. One is if we put something like y equals 3 to the x power minus 2. If we put that outside, that minus 2 outside, what that does is it takes this point right here and it moves this point down 2 spaces. It takes this asymptote line and it moves it down 2 values. And so the entire graph will be the same, but it will be going down 2 units in the y. And so that is going to shift it downward 2 units. So that anything outside, minus 2, if it was plus 4, it would shift it upward 4 units. So this is going to shift it up or down. And I always like to start with this point right here and then go to the asymptote. There's something else you could do rather than shifting it up or down, and that's shifting it left or right. So how are we going to shift it left or right? Well, if we have something like this, y equals 3 to the x, let's say plus 2, okay? Think of where that value becomes 0. Where is that going to be 0? When x is equal to negative 2, that negative 2 plus 2, so when x is equal to negative 2, that y is going to be equal to 3 to the 0 power, or 1. So at negative 2, we're going to be 1. So that actually shifts it to the left. So you can see right here, when that value is right next to the x, it shifts it left or right. And so this shifts everything to the left. The entire graph is shifted to the left. If it was if y equals 3 to the x minus 2, it would be shifted to the right 2 units. And that is our transformations of graphs. Okay. Now, one of my actually my favorite number is the number e. And you might say, 8. E's a letter, not a number. No, e is a number. Just like pi is a number, it's irrational. E is also a number, it's irrational. It's named for Leonard Euler, or Euler. He is one of my favorite mathematicians of all time. Pretty good-looking guy. Couldn't really see very well, but and he's got a diaper on his head. But other than that, this dude is awesome. So let me give you an example of what Euler's number is. Euler's number is embedded within nature. It's another proof of God's existence, because God puts these irrational numbers into our nature, okay, into His creation, okay. And so let's say we start with $1, and we're going to get 100%. 100% bonus on it, 100% of compounding. And let's say it's compounded in 1 year, well, just once. Obviously, if you get 100%, you're going to end up with $2 at the end of the year. But if you're compounded semi-annually, which means you're compounded every 6 months, so at 6 months, you have some interest compounded, and then, of course, the next 6 months, you're working on more money, which means if it was compounded twice, semi-annually, you're going to have it, $2.52. Okay, and so on, a little bit of change. If you're compounded monthly, it's going to be $2.61. Okay, you get more money if you do it monthly because every month you're getting some interest on more and more and more and more money. If you compound it daily, it's going to be $2.71. Okay, and some change. If you do it hourly, it's going to be $2.72, and hopefully you can see why credit card companies end up doing everything daily. Is they don't really care about the fraction of a cent. They're making a lot of money off you. But if you do it minutely, that's how many minutes in a year. Secondly in a year, millisecondly, microsecondly, you can see, take a look at this number. It's continuing to converge to 2.71. And if it was done infinitely, we would end up getting at 2.7182818285, and that number never repeats, and that is the number E. That is the number E. Just like pi is 3.14159, E is 2.71828, and it keeps going on forever. And so we have two formulas. This is the formula for the interest you would have. This P is the principal, how much money you put in. The R is the rate of your interest in a decimal form. So if you're getting 3% interest, you would get 0.03 right there. This is the number of times you compound it. So if you're compounding it daily, it would be 365, and N is also the number of compounding. T is the time in years. But if you're compounding infinitely, this N number is an infinite number, and that ends up becoming A is equal to P, that's your principal, E to the RT, and there's your number E that is stuck in the infinite. Now you might say, Aiton, credit cards do monthly. Daily. Credit card companies compound it daily, which means if you owe the credit card company something every single day, you're getting more and more and more interest, and they're making more and more and more money. What company would do something infinitely? Well, it's called creation. Our creation, if you're talking about a virus will compound infinitely. Okay, it compounds just an amazing rate, and it grows and grows and grows and grows and grows at an infinite rate. And so you have A is equal to P E to the RT. Think of something that decomposes infinitely. Okay, think of something like radioactive isotopes. Those things don't stop. They don't go, oh, let's just do it every hour. No, it compounds infinitely. And so you can see this is the green graph is y equals 2 to the x power. You can see the value right here is y equals e to the x power. It's still, when f of 0, it's equal to 1. Okay, and so if you can see, how do we know what all the graphs look like? Well, if we took a graph of y equals 3 to the x, 3 to the x would be right here. Okay, if we did 2.5 to the x, 2.5, y equals 2.5 to the x would be right here, and so on and so forth. And so eventually we would get this y equals 2.8128 something to the x power. And that is your value for E. So let me give you an example of a problem where we're trying to find compound interest. You take $12,000, you can invest it, you're going to get 3% interest. You want to know what's happened after 4 years. So A is equal to principal. What's your principal? Is $12,000. We have 1 plus R. R is 0.03. Over the number of times you're compounding. You're going to compound it quarterly. How many times is quarterly? It's 4 times. to the 4 times, we want to know what happens after 4 years, not 1 year. So let's eliminate that guy. 4 times 4 years, which is 16, because n is the number of times you're compounding it. So if you do that value, you get $12,000 times, I'm just doing this in my calculator, 1 plus 0.03 divided by 4 to the 16th power, which ends up being, after 4 years, you would be making $13,523.91, and that's what you would have after 4 years. But what would happen if we were compounding continuously, not just quarterly, not hourly, not minutely or secondly or microsecondly or nanosecondly or picosecondly, but continuously? So you would have A equals P, that's your principal, $12,000. E to the R, what's your rate, is 0.03. What's your time, is 4 years. So we got $12,000 times E. How do you know where E is? It's in your calculator. It's right next to the natural log, the ln button. And so make sure you take a look at your calculator to see that E. And what would we make if we compounded continuously? A little bit more, $13,529.96. Okay. Let's take a look at one last example here, and we're going to take a look at radioactive decay. And so carbon-14, when you die, I tell you, you're going to die someday. And when you die, you will start to lose your carbon-14 isotope in your body. And so you can actually figure out how long ago someone died by doing what's called carbon-14 dating. And you all just woke up and said, whoa, Mr. Eden's talking about dating. Let me try to really pay attention now, because I really need a date bad. And so we have y equals 10 to the 1/2 power. And the initial mass, what's your time in years after your initial mass? You would have 0 years, 5,730. Let me ask you, what's 1/2 power to the 0 power? 1/2 to the 0 power, that's equal to 1, which means 10 grams is what you initially start with. Whatever number here is what you initially start with, just like with your money. And so let's go to B. How much initial mass is present after 80 years? So we have y equals 10, 1/2, 80 divided by 5,730. And so we have 10 times 0.5 to the 80 divided by 5,730, and we end up getting, we have 9.90 something grams left. We got a lot left after 80 years. Because think about it, in 5,730 years, that 10 grams becomes cut in half. So think about it, we have 10 grams. It's in 5,730 years, you're going to get 5 grams. Then in another 5,730 years, you're going to be 2.5 grams. And it's going to keep getting cut down and down and down and down. You'll never hit 0. It's going to asymptote at 0, but you're never going to hit 0, because there's always at least one isotope, one atom left. Okay, and so how much is present in that? Let's say we're doing carbon-14 dating on a dinosaur bone. Okay, and guess what? We've found lots of carbon-14 in dinosaur bones and dinosaurs fossils and things like that. So let's take a look. We have 65 million years, so 65,000,000 divided by 5,730. If you do this on your calculator will spit out 0. You basically have nothing. You don't have nothing. There's still at least one atom left, but you basically have nothing. So using carbon-14 dating, if you go to a natural history museum and you ask, how did they figure out that that dinosaur was 65 million years old? And they say, carbon-14 dating, you can say, take a pre-calculus class with Mr. Aiden. So this is our first installment of exponential functions and their graphs. Have a good day, guys.